Mastering fault tolerance design. System architects obsessed with operational excellence prioritize survival over perfection. When designing a system that prioritizes operational excellence, what is the primary goal that its architects and engineers strive to achieve through the incorporation of fault tolerance mechanisms, which ensure that the system can continue to operate and provide services even in the event of component failures or other disruptions? The primary goal that architects and engineers strive to achieve through the incorporation of fault tolerance mechanisms in a system that prioritizes operational excellence is to ensure that the system can maintain its desired performance, availability, and responsiveness in the presence of failures, errors, or other disruptions. This means that the system should be able to continue to operate and provide services to users with minimal or no interruption, even when one or more of its components fail, or when there are errors in the system's design, implementation, or configuration. To achieve this goal, architects and engineers incorporate various fault tolerance mechanisms into the system design, which enable the system to detect, contain, and recover from faults or failures with minimal impact on the system's overall performance and availability. These mechanisms include redundancy, replication, load balancing, failover, checkpointing, and rollback recovery, among others. Redundancy, for example, involves duplicating critical components or systems to ensure that if one component fails, the duplicate can take over its functions with minimal disruption to the system. Replication involves creating multiple copies of data or services to ensure that if one copy is lost or becomes unavailable, the system can continue to operate using the remaining copies. Load balancing and failover mechanisms are designed to distribute workload across multiple components or systems, so that if one component fails, the workload can be redirected to other available components with minimal disruption to the system. Checkpointing involves periodically saving the system's state, so that in the event of a failure, the system can roll back to a previous checkpoint and recover from there. Architects and engineers also implement fault detection and containment mechanisms to quickly identify and isolate faulty components or systems, preventing the fault from propagating and causing wider system failures. This includes implementing monitoring and logging mechanisms to detect anomalies, errors, or failures, and taking corrective actions such as restarting or replacing faulty components. In addition to these mechanisms, architects and engineers also focus on designing systems that are highly available, scalable, and maintainable, with features such as self-healing, automatic backup and recovery, and continuous monitoring and improvement. This includes designing systems that can automatically detect and correct errors, and that can scale to meet changing demands and workloads. Furthermore, architects and engineers prioritize operational excellence by establishing robust incident management processes, which enable swift detection, reporting, and resolution of incidents or disruptions. This includes establishing clear roles and responsibilities, defining incident response procedures, and providing training and resources to support incident management teams. Ultimately, the primary goal of incorporating fault tolerance mechanisms in a system that prioritizes operational excellence is to ensure that the system can deliver high-quality services to users with minimal disruption, even in the presence of failures or errors. By designing systems that can detect, contain, and recover from faults, and by prioritizing operational excellence, architects and engineers can build systems that are highly available, reliable, and responsive, and that meet the needs of users in a rapidly changing and increasingly complex technical environment.